Hey there. So we're solving trig equations again. And if you take a look at this one, something I'd like to point out to you. You're solving the sine of 2 theta equals a half. What I'd like to point out to you is this. The theta has a coefficient of 2. Normally, when we solve for theta, it has an imaginary 1 in front of it. So we solve for single angles. This happens to be a double angle. Now, the great thing is this. We solve it the same way that we have solved other trig equations. We make certain the trig function is all by itself. So when I take a look at this particular equation, the sine function is on the left-hand side of the equal to sign, and it is by itself, right? Okay, and so now our typical process is, once we have that identified, the trig function's by itself, we need to actually find the reference angle. And if I take a look, I'm talking about the sine, and the answer is 1 over 2. That refers to your 30, 60, 90 degree triangle, right? Because a 30, 60 degree triangle has the numbers 1 and 2 on it. So, do you see how quickly I drew that triangle? That's how quickly you need to be able to draw it as well, all right? So, the sine of which of these two angles is going to give me 1 over 2? Remember, sine is opposite over hypotenuse. So if I look at the 30 degree angle, opposite over hypotenuse is going to give me 1/2. So my reference angle here is a 30 degree angle, but I want it in radians, so that would be pi over 6. Good? And then we look for our quadrants. Well, since this is a positive, sine refers to the y's. Y is positive in which quadrants? Good. Quadrants 1 and quadrant 2. Which would mean that in quadrant 1, theta would be pi over 6. Lovely. And in quadrant 2, excellent, 5 pi over 6. And typically we'd be done at this point. We're like, well, there it is. Got it. We're good. However, the 2 in front of that theta changes these parameters a little bit. Because technically, if you think about it, if this is a 2 theta, then this would double. Well, that would still be 0. And this would double, which would be 4 pi, which means I'm not just going once around the circle. Yeah, I'm going twice around the circle. So, how do we compensate for that? Whenever you have a number in front of theta that's not a 1, here's how you compensate for that. In front of this theta, I'm going to put the 2, right, because that's what's there. And here's how we compensate. Plus 2 pi k. What's 2 pi refer to? 2 pi is once around the circle. K is going to tell me how many times around the circle I'm going to go. Because there's a 2 here, we're assuming we're going to go twice around the circle. Good? Same thing over here. I've got to put the 2 back in front of the theta, and I add 2 pi, which is 1 full circle, 1 full revolution, and k is the number of times around the circle we're going to go. Good? Yeah, this is the only part of solving a trig equation that's a little bit different, and you kind of have to wrap your brain around the fact that since this theta isn't a 1 theta, the coefficient is also going to change this restriction. Yes? Okay. Now, stay focused. Let's work on the quadrant 1 angle. Stay focused. What are we solving for? We're solving for theta. So technically I need this theta by itself. So what do we have to do to get theta by itself? Yeah, we're going to have to divide by 2, which means we divide this by 2, and we divide this by 2. We divide both sides by 2. Are you with me? So you just have theta. Okay, side work. Pi over 6 divided by 2. It's the same as multiplying, by a half. That's pi over 12. Okay, so pi over 12 plus pi k. And now, remember, the k is how many times around the circle you're going. So if we just start around the circle, we're just getting started, right? We haven't gone anywhere. We haven't made a full rotation. We're just starting around the circle. If k is 0, then theta is going to be pi over 12. But remember, we're assuming we can go at least another rotation around the circle. And if k is 1, that means you're taking pi over 12 and adding pi to it. Well, make pi into a fraction. That would be 12 over 12, wouldn't it? So this would be 13 pi over 12. Agreed? Okay. You know, I know what the restriction said, but I'm going to test something out. What happens if we go twice around the circle? I mean, k is 2, so we're making another rotation around. We're like starting into rotation 3. That would be pi over 12 plus 2 pi. Remember the original restriction. The original restriction says that you're going from 0, that theta, 1 theta is going between 0 and 2 pi. This is a single theta, which means it has to stay in the restriction. It can't go over 2 pi. Well, if you add 2 pi to pi over 12, yeah, you're already heading over 2 pi, which means you can't go this next rotation around. Good? Okay. How about the quadrant 2 angle? So, get theta by itself, which means you're dividing by 2, right? Dividing by 2, which means you're going to have theta equals, now, if you put a 5 in front of this, wouldn't that be 5 pi over 12? Excellent. Plus pi k. And now I'm going to do the same process. We're just getting started around the circle, which means you're going to take 5 pi over 12 and add, 0. Okay, just that, 5 pi over 12. What happens if we start into that next rotation, right? Theta is going to be equal to 5 pi over 12 plus pi k. Well, common denominator. Whoops, I'm so sorry. You're right, we don't need the k because we said k was 1, didn't we? Which means you're taking 5 pi over 12 and just adding pi, right? See, this is why you guys need to do this stuff with me. Okay. Common denominator, 12. So 12 over 12 plus 5 over 12, 17 pi over 12. Excellent. You know, I'm going to try one more time. And when I try that one more time, k is now 2. And I'm talking about 1 theta. I can't go over 2 pi. This is going to throw it over 2 pi. So in this particular case, I have 4 solutions for theta. I have theta being pi over 12, 3 pi over 12, 5 pi over 12, and 17 pi over 12. Cool? Okay. Let me give one more thing in here. Let me do a little check. Because some of you are like, all right, those are a little bit wonky. I don't quite get that. Why is it over 12 when the original was pi over 6 and 5 pi over 6? Hang in there a second. Sine of 2 theta is 1/2. Well, if theta is pi over 12, 2 times pi over 12 would just be pi over 6, wouldn't it? And if you're like, yeah, but what about the 13 pi over 12? Okay, well, 13 pi over 12. Let me erase this, and let me make it a 13. That'll make it 13 pi over 6. That's still under 2 pi, right? And you're like, yeah, but, well, excuse me, it's not under 2 pi, but watch. 13 pi over 6, what, that goes in there twice? The 6 goes into 13 twice with 1 left over. So I'm going 2 pi, and then another pi over 6, which ends me up still at the pi over 6 mark. It just went once around the circle and another pi over 6 to get there. Twice around the circle. That's what the 2 theta meant. Are you with me? I could do the same thing with these two, and both will take me back to 5 pi over 6. All right? So I'm just showing you that your original answers of pi over 6 and 5 pi over 6 are correct. They're a little bit hidden in the answers, but when you plug them back in, they come back again. You see them again. You see the pi over 6 again, and you'll see the 5 pi over 6 again. Cool? Okay, so I have a couple of examples coming your way. Work on them, and after you work on them, go find my answer key video. Cool? Catch you on the flip side.